The normal distribution manifests in various real-world contexts, such as measuring heights across different populations, illustrating its extensive relevance. This underscores the importance of the bell curve within the realm of statistics. The Central Limit Theorem asserts that as the number of random variables grows, the distribution of their sum converges towards a bell curve, irrespective of the original distributions involved. This concept forms a cornerstone in statistical inference. Furthermore, the video highlights that grasping the Central Limit Theorem enables predictions concerning outcomes, such as the total results from multiple dice rolls, thereby refining decision-making rooted in probability. This has noteworthy applications across diverse fields. Through simulating the act of rolling dice, we observe that as more dice are added, the resulting distributions increasingly mirror a bell curve. This serves as a compelling illustration of the Central Limit Theorem in action. Interestingly, disparate starting distributions, whether uniform or skewed, ultimately yield similar bell-shaped results when summing multiple samples, reinforcing the theorem's broad applicability. Moreover, understanding mean and standard deviation is vital, as they play a crucial role in quantitatively describing how the Central Limit Theorem influences distributions over time. Variance is computed by squaring the deviations between each value and the mean, simplifying mathematical management. This approach emphasizes larger discrepancies more prominently. In contrast, standard deviation, which is the square root of variance, provides a more intuitive measure of spread, facilitating comprehension within contexts such as probability distributions. The interplay between variance and standard deviation is particularly significant when adding random variables. While variance accumulates, standard deviation does not add in the same straightforward manner. The standard normal distribution, characterized by a sigma of 1, is instrumental in interpreting various statistical concepts. It streamlines calculations related to probabilities and statistical inference. A solid grasp of mean and standard deviation equips us to effectively describe any normal distribution. These two parameters are essential for predicting outcomes and analyzing data trends. The Central Limit Theorem states that as the sum of random variable sizes increases, the resulting distribution approaches a normal distribution, which holds true regardless of the original distribution's shape. Additionally, understanding normal distributions is facilitated by the empirical rule, which states that roughly 68%, 95%, and 99.7% of values lie within 1, 2, and 3 standard deviations from the mean respectively. However, the assumptions underlying the theorem include the independence of variables and identical distribution. Breaching these assumptions can yield varying outcomes, as effectively illustrated by the Galton board example. Finally, the importance of finite variance cannot be overstated. Infinite outcomes may lead to divergent calculations of variance, potentially resulting in distributions that deviate from normality despite initial expectations.